Did you know that the atom is the smallest functional unit of matter? After that, it's broken down into protons, neutrons, and electrons that don't have any elemental properties. Hi, and welcome to our lesson on the structure of matter and atomic bonding. So here are some terms that we should remember from Science 10. And the first one is element. So the element is a pure substance consisting of only one type of atom. And then when we break down our atom, we have a proton, which is a subatomic particle, so smaller than an atom, located in the nucleus of all atoms with a positive charge. And the number of protons in an element is always equal to the atomic number. A neutron is a subatomic particle with approximately the same mass as a proton, but with no electric charge. And again, it's located in the nucleus of all atoms. An electron is a subatomic particle with a negative electric charge located outside of the nucleus in the orbitals. And they're more than 1,800 times smaller than protons and neutrons, having a mass of only 9.11 times 10 to the negative 28 grams. An atom is the basic building blocks of all matter, so it's the smallest form of an element. Once we break things down into the subatomic particles, they now no longer have the property of any element. An ion is an atom or molecule with an electric charge due to the gain or loss of electrons. So one of the electrons or more has been added or removed, leading to an electric charge on an element. Valence electrons are electrons located on the outermost energy level, or the valence energy level, and these are the electrons most likely to be involved in a chemical reaction. Then energy levels are specific orbitals in which electrons are located that are different distances from the nucleus. The larger the number of energy levels, the farther it is from the nucleus. So we're going to start off talking about Bohr diagrams. So Bohr diagrams are used to show the location of all the subatomic particles. So this includes a series of rings to represent the electron energy levels, a circle representing the nucleus with the number of protons and neutrons written inside it. And then a dot represents each electron on the different electron levels that are there. So the amount of electron energy levels depends on the amount of electrons in your atom, because each energy level can only hold a certain number of electrons. So we're going to look at the Bohr diagram for oxygen. So to figure out how many rings you need around the nucleus, look at what row the element is in the periodic table. So because oxygen is in the second row, we need 2 energy levels. The amount of electrons we can place inside ring goes as 2, 8, 8 for the first few rings. So dots in the outermost valence shell. So when we're looking in the outermost valence shell, count how many spaces the element is from the left side of the table. So from the left side of the table, oxygen is 1, 2, 3, 4, 5, 6. So that means we're going to have 6 dots in the outer energy level. You can also start adding in your electrons at the beginning. We start with 2. And for oxygen, because it has an atomic number of 8, needs 8 electrons for us to draw its atom. So that would leave 6 for the outer valence level. And there's also a missing number of electrons here too, which the oxygen atom must gain or lose to reach the atomic number of the nearest noble gas. So the nearest noble gas is neon, which would have 10 electron levels. So if we added electrons, so if we added 2 electrons to our oxygen atom, we would end up with oxide, which is the oxygen ion with 2 extra electrons. So for a Lewis dot diagram, we are going to focus only on the outermost valent energy level, or the valence level, since this is the only level capable of undergoing a chemical reaction in a chemical compound. And the symbol for the element represents the nucleus. So we still have our circle with the protons and neutrons written inside it. However, we don't need to put all the energy levels in our Lewis dot diagrams. So the symbol for the element represents the nucleus here. So we have hydrogen, H. Then hydrogen has only 1 electron, So we're going to draw that one electron above the sign for the element. When we look at phosphorus, which in a Bohr diagram would have 15 electrons, and calcium, which in a Bohr diagram would have 20 electrons, that's a lot of electron energy levels to draw as well as electrons to draw. So we're just going to arrange them around the symbol for the element. So phosphorus, if we counted how many electrons were in its outer valence level, we have 5. So we're going to put 1 in each kind of square position, north, south, east, and west. And then once we need more than 4, we're going to start to double them up. So phosphorus has 5, where calcium only has 2. So we only have 2 dots surrounding that calcium symbol. So when we're drawing Lewis dot diagrams, the first thing you're going to do is you're going to write the element symbol to represent the nucleus and any filled electron shells. So here's chlorine. Now, chlorine, if we looked at our periodic table, is going to be the 7th element over from the left, so it's going to have 7 valence electrons. So we're going to go around and use a dot to represent each of the valence electrons, and they are in groups of 2, roughly, going around that element symbol. So except for helium and hydrogen, who only have 1 energy level that can contain 2 electrons, the element's valence shell has the availability to hold up to 10 electrons. So, up to 8 electrons. So that's how many we can have between 1 and 8 electrons in our Lewis dot diagram. So we want to start by placing valence electrons into each of the 4 different orbitals. So 1, 2, 3, 4. And then if we need additional ones, like we said, chlorine needed 7, we start to fill them up until all the positions are occupied. So 1, 2, 3, for a total of 7. So we look at the Lewis dot diagrams for the elements in period 2. We have the outer valence level. So lithium has 1 element in its outer valence level, beryllium 2, boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, and neon as a noble gas, a full 8 in its outer valence level. So now we're going to fill in the dots for the elements in period 3. Sodium has 1, magnesium 2, aluminum 3, silicon 4, phosphorus 5, sulfur 6, chlorine 7, and argon 8. So when we look at this across the periodic table, the amount of valence electrons in the outer shell stays constant for row 1 through row 8 of our periodic table. Sorry, column 1 through column 8 of the periodic table. So we see a very similar electron arrangement. So when we are recalling that the atom, the number of protons and electrons are equal, meaning that our element has a neutral charge, and this means that the valence energy levels are not always necessarily full. So the atoms are capable of gaining, losing, or sharing electrons to try and become more stable. And an atom is most stable if its outermost valence electron shell is full. So neon is going to be the most stable element, where both lithium and fluorine, incidentally, are going to be the least stable element, fluoride, because fluoride needs 1 electron, lithium wants to get rid of 1 electron. So because they're closest to being full or empty, they're going to be the least stable elements. So an atom will do whatever is easiest to achieve a full valence orbital. So nitrogen will gain 3 electrons to be stable, like the neon gas. Oxygen will gain 2 electrons to be stable, while fluorine will gain 1 electron to be stable. Now, for aluminum, it would need to gain 5 electrons, which is a lot of work. So instead of gaining electrons, aluminum is going to lose 3 electrons for it to become more stable. So if an atom has 3 or more to gain, it will do that. If it has 5 or more to gain, it's typically going to lose electrons to become more stable. So magnesium is going to lose 2 electrons, and sodium is going to lose 1 electron to become more stable. So looking at terminology, metal atoms are always going to lose electrons to become more stable. And so they're going to become cation with a positive charge. And I remember that cations have a positive charge because they have a T in the middle of the word, and a T looks like a plus sign. So they're going to join with a nonmetal to make an ionic compound. Now, this is a compound between a metal and a nonmetal. Nonmetal atoms are going to gain electrons. They'll become an ion with a negative charge known as an anion because it's less work for them to gain 1, 2, or 3 electrons than to lose 4, 5, 6, or 7. Anions, which are negative, will combine with positive cations to form ionic compounds with ionic bonds. Two nonmetal atoms can also share electrons with each other to form molecular compounds with covalent bonds. Typically, particles with the same charge, like if there was two positive ions, they're going to repel each other, while particles with opposite charges, one positive, one negative, are going to attract each other. Electrons, because they're negative, are attracted to positively charged protons in the nucleus of their own atom. But the closer the electron is to the nucleus, the stronger the attraction. So this is why valence electrons, because they're furthest away from the nucleus, are easiest to give away by an atom because they're not as closely attracted to the nucleus as the other electrons. So, valence electrons are attracted to the positive nucleus of other atoms because they can get closer to them. So, when the atom loses an electron, another atom has the space in that valence, that another atom that has space will be able to pick it up. So, sodium is not full. It has only one valence electron, so it could lose one or it could gain seven. Where chlorine has 7 of 8 electrons. So, to become more stable, it could gain one electron or lose seven. Okay, which one do you think is going to be more work for the atom? So, that chlorine that needs one atom and the sodium that needs to lose one atom can bind together in a molecular or an ionic bond to form sodium chloride. Now, once they're bonded together, both valence electrons rings are full, leading to a more stable compound. So, when we're looking at properties of atoms, elements, and compounds, we can look at the physical properties as well as the chemical properties. So, physical properties are aspects that can be observed or measured without changing it. So, we can look at the color, we can shine a light through them and see what kind of crystal radiation is formed or crystallography is formed. Where chemical properties can only be measured by performing a chemical change. So, how does that substance behave in a chemical reaction? Like, does it burn? Does it melt? Or does it burn? Does it bubble? Does it change color when added to other chemicals? So some physical properties include the color, the state, is it a solid, liquid, or gas, its volume, mass, or density, so we can weigh it, we can see if it floats, and then its boiling and melting point, because those changes of state don't actually affect the element. Examples of chemical properties include the pH value, the toxicity, its ability to burn, and its reaction with water, acids, heat, and or litmus paper. Well, chemical properties of metals include, does it react with water and air? So they will oxidize. We have aluminum will obviously oxidize white, where iron oxidizes and forms rust. Metals can react with acids and they produce hydrogen gas. So we'll see bubbles being produced as well as a change in pH. And metal atoms will give away electrons in order to become more stable. So they'll become cations, which are positively charged. Again, there's that T in the middle reminding us that it's like a positive ion. Metal ions also will react with nonmetal ions to form ionic compounds, such as sodium chloride or magnesium sulfate. Metals are typically solid at room temperature, except for mercury. They're mostly gray and silver, shiny. They're malleable. We're able to bend them into shapes without crumbling. They're ductile. We could stretch them without them snapping. And they're conductive, so they can transmit both electricity and heat. So a solid piece of metal is formed by positive ions attracted to a set of free moving electrons. So since those like charges repel, the electrons act as a buffer or glue to keep all the positively charged metal nuclei together, forming a sheet like aluminum foil. And this is what gives metals their distinct physical properties of like ductility, malleability, as well as conductivity. Chemical properties of nonmetals include they react to form oxides that are acidic. So their pH will be less than 7. They're good oxidizing agents, which means they can take electrons from other substances. And again, this makes sense because they typically will need 3, 2, or 1 electrons to become stable. So they're going to accept electrons easily from other substances. Now, when they do this, that nonmetal atom becomes a negatively charged ion called an anion. And the exception of this is the nonmetal noble gases because they already have a very full valence level, so they're very stable. So nonmetals can either react with metal ions to form ionic compounds, or they can share electrons with other nonmetals to form molecular compounds with a covalent bond. Nonmetals can be solid, liquid, or gas at room temperature. So like sulfur is a solid where oxygen's a gas. The color varies between different elements. They're typically dull. They're not malleable or ductile. They're brittle. So like sulfur will crumble. And they're conductive. So they are not conductive. They're an insulator. So heat and electricity does not easily transfer through them. Salts are naturally occurring ionic compounds that have very strong ionic bonds between the two ions, so like sodium chloride or table salt. Now, this is because the electron from sodium's valence energy level is now part of chlorine's valence orbital. So it's a solid, um, it's a stable ionic compound. Now, salts are solid at room temperature. They're generally white and they often dissolve to form clear, colorless solutions. They're not malleable or ductile, so they'll break if they're struck. They do, however, dissolve well in water, and they are not conductive as a solid. However, when they're dissolved in a solution, they're very conductive. So this is known as an electrolyte. So ions in a salt will organize themselves into alternating positive and negative ions to form crystals, which will be referred to as a crystal lattice. Now, since these like charges repel each other, the cations and anions alternate so the particles can stay together. So, like metals, this arrangement is what gives them their distinctive physical properties of being able to dissolve in water, as well as being brittle. So, plastics are large hydrocarbon molecules. So, hydrocarbons are organic molecules made up of carbons and hydrogens held together with covalent bonds because they're both nonmetals. Covalent bonds are not as strong as ionic bonds because the electrons are only shared between the two nonmetals. They're not completely transferred one to the other. So they're typically solid at room temperature. Their color will vary, and they're not conductive. They're an insulator, which is why we have lots of plastic cooking utensils. They're highly flexible and non-soluble, but they could be permeable or non-permeable. So materials can enter their pores or not enter their pores. So since there's no positive and negative ions in a plastic, they don't form a crystal lattice, which again allows them to be pliable. So instead a Lewis dot diagram shows the sharing of electrons in large molecules like plastics. So the hydrogen and carbons are sharing the one atom that or one electron that the hydrogen has. So their arrangement and bonding pattern is what gives them their distinct physical properties. So when we look at arrangement and bonding, how does this explain the properties of matter? So the melting point is the temperature at which a given solid will undergo fusion. So since energy is required to raise the temperature of a solid in order to make a substance melt, and the stronger the bonds are between different organisms, the higher the melting point. So phase changes occur when the heat energy no longer increases the temperature of a substance, but breaks apart those bonds between the ions to change them into a liquid. So since ionic bonds are very strong because that electron is transferred from one molecule to another, it takes the most heat or energy to break them apart, which is why they're all solids at room temperature. Covalent bonds are weaker, so molecular compounds tend to have lower melting points because they don't need as much energy to break them apart. Metals typically have higher melting points than molecular compounds because of the strength of the metallic bond, but a lower melting point than ionic compounds because ionic compound bonds are stronger than the bond of molecular metallics. So when we look at some of the physical properties, we have flexibility, which is the ability to bend without snapping. So ionic compounds, they have a very strong bond. However, they're not flexible because the ions are oppositely charged. So when an ionic compound is bent, the like charges are forced together and they don't want to be together. So as they internally force themselves apart, the compound is likely to snap. Molecular compounds are flexible because they do not have opposite charges, so the shared electrons migrate around the nuclei and hold the ions together no matter where they're bent to do. So they're able to move those charges around so that they can stay together. Metals are also flexible because of the sea of free electrons that's meant to protect the positive nuclei from coming too close together, are able to move and allow the metal to be formed into different shapes. So, conductivity is the ability for heat or electrons to pass through a specific material. Now, the ability to conduct electricity depends on free electrons. So, ionic compounds and metals are good conductors because they both have free electrons. Molecular compounds are insulators because there's no free electrons. Those electrons are shared between the compounds. So, looking at a quick summary of the properties of matter. So, we have salt, which is sodium and chloride. It's an ionic compound forming ionic bonds. So, it's brittle, soluble in water, but has a high melting point, and in solution, it conducts electricity. Plastic is made up of carbon and hydrogen. So, it's a molecular compound with covalent bonds, meaning it's flexible with a low melting point. It does not conduct electricity or heat, and it is insoluble in water. Aluminum foil is made up of the aluminum atoms. It's a metallic element with metallic bonds, and it does conduct electricity and it's malleable. It has a high melting point and it's insoluble in water. So I hope you enjoyed today's lesson on the structures of metal and structures of elements, compounds, and bonding.